Welcome to the CASI talk with our guest Jim MacLeod. I'm Lou. I guess I'll kick us off for everything, and thanks for hanging with us for through our technical difficulties. So, and I'll pass the floor to Jim.
Thank you very much. Good evening. My name is Jim MacLeod, and they affectionately refer to me as the Iceman. I'm not wearing my cape tonight, just to keep the disguise going, but I was in that seat 41 years ago, or 141 years ago, depending on who you talk to. So I actually started here. I started as a graduate student at NRC, working under Professor Sarvanamutu here at Carleton, who some of you may have heard of, or at least remember him. And I only intended to stay at NRC for 1 year until I finished my my master's, and then I was going to go and work for a gas turbine company somewhere out there. And 41 years later, I'm still sitting in the same desk in the same place. So that's how things change. So I'm going to be talking tonight a little bit about engine icing certification. This is gas turbine engines, specifically not piston engines, but specifically for aircraft use. So it'll be something that you may be surprised at the effect of what ice can do. So we'll start off here by page down. Nope, that's not it. Just click on. Interesting. It's not page down. Okay, just click on it. Oh, off to the side. Okay, all right. So I'll give you a little outline here. We'll talk a little bit about what the icing threat is to engines specifically, also aircraft. We'll talk about what are the current airworthiness requirements that are specified by 3 agencies: the FAA, which is the American group, the Federal Aviation Administration, that oversees airworthiness for all things that fly. EASA, which is the European version of that, and Transport Canada, which governs anything that flies in Canada. They all generally work with each other and sort of harmonize with each other, but not always. We'll talk about what we call the standard icing envelope, which is defined by the FAA as a Part 25 Appendix C, which tells us what type of a cloud the aircraft is going to be flying through and how we should simulate it. We'll talk about the 2 main types of ice, rime ice versus glaze ice. They are different. They behave quite a bit differently, and they can result in different problems for the engine. I'll talk about some of the new icing requirements. When I say new, I mean Appendix C icing goes back to the 1950s and 60s. The ice crystal requirements have only been recently added within the last 10 years. I'll show you some pictures of some engines of the past that were certified and all the issues that were associated with them. We'll talk about some of the present day engines and the issues that they have, which are different. And then what are going to be the problems related to ice engines that are being built for the future. They have a whole new range. Every time you come up with a solution, it introduces new problems. So there will be always problems, and there will continue to be, which is good for me. I get to keep working for another 40 years, or sorry, 39. And we'll talk about some of the engine icing facilities, which are in Canada and other parts of the world. Actually, the majority of them are in Canada. We'll talk about some of the challenges which the facilities are facing themselves to be able to meet the new demands. And we'll also talk about some of the challenges that the engine designers have in terms of being able to get an engine successfully through the certification process. And then we'll wrap it up. Okay, what are the particular threats? Well, there's sort of 4 groups here. There's permanent damage resulting from the impact of ice or jamming of ice. The ice is incompressible, meaning if it gets jammed between a rotating piece of machinery, like a titanium blade, and a casing made of stainless steel or titanium, the ice is not going to give. either the blade is going to bend, or the casing or the treatment of the casing is going to give gouged out. That's the problem. Ice, well, you can't compress it. So something has to give way, and that very expensive blade is going to bend and look like that in a blink of an eye. And so that's bad, obviously. Going to result in permanent damage, which means the aircraft would have to be grounded and engine repaired. It also tends to be, being a very abrasive, it can actually take out abradable seals like the sealing material on the casing, the fan track liner, which is sort of an acoustic liner around the fan. It'll actually, the ice coming off and hitting it will actually chew it up, even though it's made out of stainless steel or sometimes aluminum. So that's all permanent damage, which results in loss of performance and require repair to be done. There's excessive vibration, which happens when the rotating parts, namely the fan, which is the front of the engine, ices up and then starts to shed ice unevenly. So now you have an imbalance, a significant imbalance, and vibration starts to occur, which will permeate through the entire aircraft. We test these engines in our facility here in Ottawa, and the walls are 3-foot thick concrete. My office is located at the far end of the building, and when engines are shedding ice, I can hear it and feel it in my office. So it actually is. So if you're on the aircraft, everybody on the aircraft is going to know that this is happening because you can feel it. It permeates through the entire plane. Those billionaires flying in their private jets do not like to see ripples in their scotch, so the vibration is not something that they appreciate. It actually can get so bad that pieces on the engine can start to break. I've had starters fall off. I've had fuel lines and oil lines break and the engine spew its oil all over the floor. Fuel lines breaking, fire starting in the engine because of broken fuel lines. So all of that falls under the general category of bad. Yeah. Anyway, that can result in a crash. So then there is also the possibility that ice, as it builds up on the front of the engine into the core of the engine, where it gets quite small, ice builds up in there, and it actually reduces or chokes the air going into the compressor, and therefore the turbine, which is at the other end of that chain, is not getting enough cooling air to it, and the turbine starts to melt. That's under the general category of expensive. And of course, there are the other is a dynamic response. So engine may stall because of ice, which releases inside. The engine gulps a large amount of ice in one shot, which will result in the combustor flaming out, or a surge in the compressor, which may also result in a flame out, or a big ball of flame coming out the back end, which people sitting in the seats behind the wing don't like to see that. And again, the pilots are not too happy with that too, because that means the engine has to be restarted, which is never an easy thing to do when you're in critical flight periods. So anyway, all of these are results which are common or have been common, and they are not going away. They're not getting there. There's been improvements, but they still happen, and they're happening with some increasing frequency due to the design of current engines. So here's an example. The picture on the left over here, that's the front of the engine with the ice buildup, and moments later the ice shed, and something happened. And when we took it apart, this is what it looked like inside. Now, for those of you who don't know what a gas turbine looks like inside, I will tell you that this is not good. It's not supposed to look like that. There are some pieces missing here, a lot of them. All right, this engine's not going to produce any thrust whatsoever. So as I said, when ice can break things, it actually, in this case, it happened two things happened. The engine surged, a blade broke, and because the surge occurred, the air is now going forward, picks up that broken blade and basically starts thrashing it around inside and took out more than half the blades inside the compressor in the process. So that is a complete write-off of that engine.
How long does it take to stop when something like that happens?
The engine stopped real fast. Yeah, almost instantly. And that can be a problem too, because now if blades are jamming, if broken blades are jamming it and it seizes up, you now have one engine which isn't turning, and it creates a huge drag, and the aircraft is suddenly going to go turn very sharply as a result of that. So all bad. So let's take a look a little bit here at the front end. So icing is generally a problem of the front of the engine. And as I said, the standard ISO, every cloud up to 22,000 feet is made up of supercooled liquid droplets. So unlike what your teachers in school taught you, and probably still teaching you here, water does not always freeze at 0 degrees Celsius or 32 degrees Fahrenheit, okay? The water that's in the clouds that you see up there is essentially pure water. And pure water will actually go down to almost certainly below -30, in some cases -40 before it will freeze. It will self-nucleate and freeze out. So any clouds you see that are above 22,000 feet, those wispy clouds very high up, those cirrus clouds, they're all ice crystals. But everything, the white billowy clouds and the gray dark clouds that you see, those are all water, 100% water. And they exist at temperatures down to -30-ish. And the reason they don't freeze out is because they're pure water. There's nothing for the droplet to nucleate out onto. At the higher levels, there's dust. There's always dust in the upper atmosphere. It's a little dust particle, submicron is all it takes to get that droplet to freeze and form a nice crystal and grow into snowflakes or whatever. But these clouds are sitting there with water at super cool temperatures, and they stay that way until they are disturbed in some way. And that's what happens when the plane flies through the cloud. Bam, droplet immediately freezes to that cold surface. So the liquid water droplet problem is generally going to be on the fan blade here, on the stator vanes, the bypass ducts, the guide vanes, and potentially 1 or 2 stages into the compressor here. The lip, separate splitter lip as it's called, ices up pretty bad. Once you get past this point, the temperatures in the air in there are above 0. So at that point, there's going to be none of the super cool liquid is going to freeze, and it's just going to now turn to vapor, and it's fine the rest of the way through. The ice crystals, on the other hand, they are going to bounce off these cold surfaces. They don't stick to it. So they bounce around, and the ones that go out the bypass duct go out and they're gone. But the ones that happen to make it into the core here, once they get into around this area all the way back to about here, they're now seeing temperatures in the +20 to +30 degrees Celsius. And that's where the problem starts for them, because then they actually start to melt, but they form a water film. And then that water film allows those ice crystals to sort of splash into it and slow down and pile up and create some real problem. I have some pictures I'll show you later, but it is in fact possible for ice to attach to surfaces which are +30 degrees. Hard to believe, but it actually can happen. Well, those are the real areas of interest when it comes to icing, but they're different, and they occur in different places in the flight envelope of the aircraft. So when one's doing icing certification, there's a whole realm of things you have to do here. There's the super cool liquid we talked about, well, droplets in the order of 15 to 40 micron, which is about 1/3 the size of a human hair. That's how small these droplets are. And we generally are spraying, we go by volumetric concentration, grams per cubic meter. 0.2 to 5 grams, which is really not that much. It really isn't a lot of water. But when we are actually spraying above 2 grams, you can't see the engine anymore. It's completely blocked of you. And we have a gentleman in the audience out here who actually got to witness that. So at those higher concentrations, it's like a total whiteout. We are also required to do an ice sheet test. Now, the ice sheet is basically to replicate the fact that when the plane is flying through this cloud of ice, there's ice not just hitting the engine, but there's ice hitting the forward fuselage, the radome, the wings, and that sometimes that ice is going to come off. A chunk of it's going to come off and by chance get sucked into the engine and potentially do some physical damage to the fan blades or whatever. So we have to, there's a prescribed size of ice slab that we actually have to throw into the engine. I love my job. I get paid to break stuff. Okay? I get paid to break an engine worth $20 million. Is that not cool? Anyway, so the other thing we have to do is shoot an ice ball, which is we do a 1-inch and a 2-inch or 25 and 50 millimeter, depending on your choice, single shot. So we have to hit a vulnerable area in the inlet of the engine, which might have an oil line or something going through it, which if it failed through to an impact, could result in some significant problem for the engine. And we shoot the ice ball, we shoot at whatever the aircraft speed is. So if the aircraft's flying at 400 knots, we shoot the hail ball at 400 knots. Same with the bird. They're birds as well. So, but that's another story. Hail, we do a hail test. So this is a hail storm test. So we actually fire a volley of hail for approximately 30 seconds, and it's usually 10 or 16 millimeter, one or the other. And we can fire 1,500 hailstones per second at up to 400 knots. You do not want to stand at the end of the barrel of this gun when it's firing, because it will.
You guys do snowball fights?
No. I would win. Who's dead? Yeah, no, this is, one of the tests we do to check, for uniformity is we put a 1-inch sheet of plywood in, after the gun, and we fire at that. And it takes 3 seconds to blow a hole the size of a garbage can through it. And there are toothpicks all over the floor, but it's fun to watch. And last but not least, we do, we do ice crystal, which I said is a problem with high altitude operations, which I'll talk more about that later under the new requirements. And snow, which is more of a lower altitude and ground type of problem, but nonetheless can result in a shutdown of the engine. This is an example of an engine which has been exposed to ice. Now, the problem with engines here is that they have no protection. The aircraft has some protection. The leading edge of the wings have either heaters or pneumatic boots, which expand to break the ice off. The windshield of the aircraft has heater, the probes on the front of the aircraft for measuring, pitot probes for measuring speed, and the tap probes for measuring temperature. They all have built-in heat protection to keep ice from building on them. The engine has nothing. So it takes whatever comes in, and there's a lot of air coming into that engine, laden with water. And so the engine has to be able to suffer it out, take all of that, and keep running. Because if the engine quits, the aircraft is going down, okay? So what does the Appendix C, the definition of the cloud look like? Well, it's basically divided into 2 categories. One is what we call continuous maximum, and that's based on what we call a stratiform cloud. So those, that sort of gray overcast day cloud, that's what we call, that's a stratiform cloud. It means it's like a layer. That's a relatively low concentration, but it extends for a long period of time. So the plane is flying through it for a long period of time. And the other is intermittent maximum, which relates to cumuliform clouds. So these are thunder clouds, vertical, a lot of the big billowy clouds that you see, which are very tall, but they're not very long. So the concentration of water is much higher, but for a much shorter period of time, which can be good or bad, depending on the case. So the appendix basically defines the characteristics of the cloud based on droplet size, the liquid water content or the concentration, the temperature of the cloud or the air, and the horizontal and vertical extent of the cloud and the altitude of it. So basically what has happened is the aircraft or the engine manufacturer has to take this and say, okay, this is the environment that the plane is going to fly through. Here's the flight path through that environment. So, and what is the engine operating at when it's flying under those conditions? And that's how they decide what test points they're going to run, what liquid water content, what temperature, what droplet size that they're going to run. So the testing is mostly done at sea level, although it can be done in altitude facilities, but that's a little difficult. So the horizontal extent really determines how long the test time is going to be, meaning how long is the plane going to fly through it, and then what the concentration is going to be and the droplet size. So temperatures that we're typically testing at are between sort of -3 and -30 degrees Celsius. Below that, again, there's none of the supercooled liquid exists at temperatures much below that, so there's no reason to test that. But that's when we're get into the ice crystal part if we're going to be doing higher altitude and colder temperature stuff. So there are two types of ice. One is rime ice, and here's an example of what rime ice looks like. It looks very snow-like. It's very white, opaque. It has a very high adhesion for it. It sticks like glue. It sticks very hard until you have to physically scrape it hard to get it to come off. But it's very low density. It's very fluffy. If you break it off, it just crumbles in your hand, just like snowflakes. But it is bonded at the subatomic level to the base material, which in this case is usually titanium. So as a result of that, because it sticks so well, it sheds partially or infrequently. So you'll get partial sheds. So some of it will come off, but not all of it comes off. So now you get that imbalance that I talked about, which can result in very large vibrations of the engine. The smaller engines, like business jet engines, are probably worse because the mass of ice relative to the mass of the fan is higher, whereas the very large fans on the big jumbo jets, that sort of thing, the mass of ice relative to the mass of the fan is less. But nonetheless, if you get a large fan vibrating even a little bit, it will scare everybody on the plane for sure. The other type of ice, no, the rime ice occurs at colder temperatures, sort of below -15 sort of thing, -12, -15. Glaze ice, on the other hand, is the warm ice. This is what it first happens when it just goes below zero, below freezing, and it starts to transition in around the -10 mark. It looks different. You can tell by the pictures. This is more translucent, more like an ice cube type of thing, and so it is much higher density, which means it's harder. And if it gets jammed between one moving and one stationary piece, it's not going to give. It's going to break one of the other two pieces. Whereas the lighter, more delicate rime ice is kind of just going to get smeared and it won't do as much because it smashes up into very small particles. This stays in chunks and it will bend things and it will break things. And I've actually seen titanium blades look like somebody took a pair of scissors and lopped it off. They literally cut. It cut through a titanium blade. So it has the ability to do that kind of damage. It's very hard. It produces these very unusual shapes. You can call either hammerhead or lobster tails. And you can see them, especially in here, where they're very intricate shapes. People have tried to model these using CFD and model that. You're not going to do it. Okay, these are very intricate shapes, and there's a lot of probabilistic effects that are going on in there, so it's difficult to necessarily quantify it. As I said, it can cause a lot of mechanical damage, both fan blades. We did a test one time on an engine which was going to be used on it's actually a 737, but it's used for anti-submarine warfare. It searches for submarines And so it flies over the ocean for long periods of time, so it's flying in a lot of moisture. And so we had to do a 3-hour test. And after about 2 hours and 45 minutes, there was a chunk of ice the size of a beer can hanging off of the nose here. And it came off and hit the compressor blade right at the tip, and the tip looked like that on 3 blades. Complete damage right off. Interestingly enough, you can barely see this sort of like a bluish piece underneath the tip here. One of the engine manufacturers decided that it was a great engineering idea to put a rubber tip on their spinner, because the idea was the rubber would kind of wobble a little bit and that would stop ice from accreting. Didn't work, but yet they still do it. Engineers. So as I said, the adhesion force of ice is dependent drastically on temperature. So at the warmer conditions down here, the ice has relatively low strength. It doesn't bond well to the substrate, and so it will come off very easily, which can be a good thing. But when it does come off, it's very hard and it's going to do some damage. As you go down in temperature down here, you can see the adhesion strength goes way up. And so it is now bonding itself very strongly to the substrate. At this point after here, there's not really much change, but now it's bonding it bonds well to the material, but it doesn't bond as well to itself. So you'll get a place where the ice will come off, but the outer layer comes off and there's a sublayer which is still attached to the metal. And that's the problem with these, is that now when it comes off later, when they have to do an acceleration after each test, if the ice is sticking more, comes off later in the acceleration, and the stall margin of the engine is lower at the higher power setting than it is at lower power setting. So if it comes off at the moment when you have the minimum stall margin, the engine's going to stall. And the reason it stalls is because when the engine is accelerating very quickly, the time it takes for the ice to come off and go through to the back of the compressor is measured in a fraction of a second. It's moving so fast that the ice doesn't have time to change from solid to liquid to vapor. It's still in solid condition, and it's hitting temperatures that are now in the order of 500 degrees Celsius at the back of the HP compressor. And guess what happens? It flashes directly from a solid to a vapor instantly. And that causes a pressure spike, and compressors don't like to see pressure spikes at the back of them. And so it drives the compressor into stall, which we'll talk a bit more later. But that is not when you want to have that happen. So what's happening? What are the new requirements in the last 10 years? Has basically focused on a couple of areas. One is the ice crystals. And as I said, those occur generally at higher altitudes. They're produced mostly, interestingly enough, within 10 degrees of the equator. And the reason that is because to get that much moisture that high up, you need to have a lot of moisture on the surface down low altitude. Canada is essentially a desert. There's not enough moisture at low altitudes to generate that. But if you go to Southeast Asia, if you go to Costa Rica, you go to certain parts of Africa, Australia, for example, there are these major storms which brew out there, and they pick up all that moisture from the ocean level and they blow it up to really high altitudes. And it then freezes out and produces these large concentrations of ice crystals. So there's been a number of events over the years. One that really stands out is occurred about 20 years ago in Manila, Philippines. 747, 4 engines. They started their descent into Manila Airport, and 3 of the 4 engines flamed out. They were able to restart them, and then 3 more went out. And they restarted those, and 2 more went out before they finally landed. 8 engine flameouts during that 15-minute descent. They said the pilots took a little long to come out of the cockpit because they had to change their underwear. I mean, you got 4 engines, you assume that you have no problem, but all engines are seeing the same environmental problem. So, you know, it isn't going to be just one that goes. They were lucky all 4 of them didn't go out, because at least with one of them running still, they could use it to restart the other 3. If they'd lost the 4th, we're talking lawn dart. Because you cannot fly a 747 on one engine. There was an example of an aircraft in Costa Rica, 4-engine again, BA-146, much smaller. But they had all 4 engines roll back at 29,000 feet. They got one of them restarted at 1,000 feet above the ocean. And they were able to keep themselves from descending any farther until they were eventually able to get another one started so they could actually get themselves back up and land quickly. But so it's a serious problem for sure. So mostly in this case, you don't see mechanical damage is less likely to be seen here. More likely to be surges and flameouts and rollbacks, and I'll talk a little bit more why that's the case. The problem now is that there aren't really any facilities available to test this requirement. It's a new requirement, but to be able to show compliance to this new rule is becoming a little bit of a problem. Fortunately, or unfortunately, the airworthiness people have said, well, we'll allow you, until there are facilities to do these tests, we'll allow you to do it analytically. Don't go flying. Anyway, so what that means though is you can't just go and you have to, if you're going to do it analytically, you have to show that your analysis is based on something which matches a real test. You have to test something, whether it might be a model or a mock-up or a component, and show that your model can predict what happened there, and then you use that to say, okay, my model works for that, and then I'm going to assume that that can be extrapolated to the entire engine and work that way. So we'll see. So the Appendix D, as it's called, this is what covers the ice crystal cloud, and it, as you can see, goes up to 50,000 feet, a little bit more, and down to -60. So most of the incidents that we see are in this realm here, although you can get some down here in more mixed phase conditions. So there's both ice crystals and typical liquid. All up here, it's below -40. You can see there's this is where it's total freeze out. There's nothing but ice crystals above that point. So this is what an ice crystal accretion looks like. And this we did in our altitude facility here in Ottawa. We were testing at 30,000 feet, Mach 0.5. In this case, the temperature of the air going through and the blade surfaces, this is a compressor blade rig, was at +10. And we're putting in 4 grams per cubic meter. This took less than 2 minutes. That much ice to accrete. That's a lot of ice. And you can see it's blocking, it's going to block significantly. This is how you get rollbacks. Rollbacks occur when the engine gets choked up so bad that there just isn't enough air going through the compressor. It's not enough to stall the engine, but the engine just doesn't produce any power. It just kind of rolls back to a sub-idle and sits there and says, I don't know what to do. Enough air to do anything. So in this case, you can see it's growing and growing. And
Not now.
Ooh.
You can have it.
Mic's open.
Okay. Anyway, so the idea then is, now this takes a very short period of time to occur. The problem here, though, is what happens if you fly out of the ice crystal cloud and suddenly there's no cloud there. The problem is that all of this ice will leave instantly. And the reason is because the buildup is occurring because of a melt ratio. There's a certain amount of liquid and a certain amount of ice. So the ice crystals are melting because the air is warm. They form a film of water over the blade surface. The ice crystals coming in behind see that film of water. They hit they splash, they slide, they slow down, and they start to pile up. And they will actually take the temperature of the blade down below freezing. And that will cause it to stick. Okay, but it's not very well adhered. It's even less adherence than the glazed ice we talked about. So it's basically just the stagnation pressure that's holding it there. And the moment that you throttle up so the temperature gets warmer, or you come out of the cloud momentarily or completely, and there's no more ice coming in, that warm air that's now flowing, this is plus 10 air flowing over it, will suddenly cause it to just go, and you now have, it only takes 25 pounds of ice to flame out a CF6, which is the engine that's on the 747. And this is the equivalent of 2 minutes worth. So that's the problem with ice crystals, is that it's a sudden release of almost all the ice goes in one swap. And then you end up flaming the engine out or surging it, and it causes the engine to quit working. Interestingly, there was a case where aircraft was flying in a new aircraft was designed. They were flight testing in Africa, and they had 4 big turboprops on it, and they were having flameouts of those. And it turned out it was a design problem of the engine, because the engine was such that it was actually mounted backwards. So the air had to come in through the inlet, go all the way to the back of the nacelle, make a 180-degree turn, and then go into the compressor. And that back surface was warm because the exhaust sort of came around the outside. And so the ice crystals would come in, try to make that 180-degree turn, see that warm surface, and they would just build up a big slush puppy in there. And then if the pilot did a throttle maneuver, it just suck the whole thing in, and the engine would flame out. So,
hi, Jim. This is Greg Chapman speaking.
hello, Greg.
Hi. I just want to make sure I heard you correctly. My speaker's a little bit muffled, I guess. I think I heard you say the test you're showing was over 2 minutes. Is that?
Yes,
right?
it took only 2 minutes to accrete that much ice. Yes.
Yes, and maybe other people know, but that's very important with regard to the assumed recognition time and activation time for an anti-ice system.
Yeah, but the problem is, and there's no anti-ice here. This would be equivalent of a 3rd or 4th stage compressor, so there's no ice protection back there at all.
Yeah, so not disputing that, but perhaps you might remember per the FARs, right?
Yeah.
They assume that there's a certain amount of recognition time by the pilot, and then response time, and then
2 minutes.
activation time, and then there's a whole bunch of margin built into that.
Yes.
So that all that stuff together is 2 minutes. So that all I'm trying to say is that's one of the reasons why 2 minutes is very interesting from an accumulation perspective. It wasn't, I don't think it's picked at random, let me say.
No.
Right.
Okay. All right. So let's talk a little bit about some of the history of engine testing. NRC was one of the first places in the world here in Ottawa to actually do an icing test on a gas turbine engine back in 1947, 3 years after I started there. And anyway, so this is so long ago that there was no Appendix C. So in those days, what it was carburetor icing on piston engines was the threat, because the ice would build up in the throat of the carburetor and essentially choke it off. But it would never, the engine would only just choke. It would never, no damage really per se to the engine. But when the turbine was introduced, of course, now there's a lot more air flowing through a turbine than there is through a piston engine. So there's a lot more ice that's going to potentially build up, and you can see that there's massive amounts of ice here. So the initial work, there was a lot of guessing, I'd call it. Well, scientific wild ass guessing, maybe is the best word to put it, swag. But they were kind of feeling it out to see, what should be the requirements for the engine. This was an engine, UMO 004, which was borrowed from the German Air Force at the end of the Second World War. And because they were one of the first ones to actually fly turbine engine, so that made sense. Interestingly enough, this was the result of that test, and I think there's, if I'm not mistaken, 8 stages in this axial compressor. That's what is referred to as a corn cob. There are no blades left, none, zero, zilch. Now, NRC prides itself in being able to be thorough in their investigation and make sure that there wasn't any issues or problems, things were done wrong. So we put another engine in. Same result. So yeah, you can see what happens when ice wins sometimes. So this was the engine I referred to flying in the Britannia. This was the first ice crystal test in the world done in 1955 at NRC. And this is a Bristol Proteus engine, which is part of Rolls-Royce now. But this is the case where the air goes in through the front here for this part, but it goes all the way to the very back, makes a 180-degree turn, and then goes in. So interesting enough, so NRC, we used to do all of icing for Rolls in those days. So they asked us to do this ice crystal test, and we came up with a system. I won't go into the description of it, but the interesting part was we were able to replicate what they were seeing in flight. And interestingly enough, they said, well, how can we fix this? And so we happened to have a group of guys in our lab who also worked on diesel engine technology. And they said, well, what if we put a glow plug in the combustor? Because nowadays all engines have an auto relight system, which if it senses a drop in temperature or pressure in the combustor, it will turn on the igniter system, fire the igniters and so on to restart it. But these engines didn't have that because they were all hydromechanical controls. So the idea was to put a glow plug. Now, for those of you who don't know, on diesel engines, there's something called a glow plug. So when you have to start it on a cold day, you have to hold the button for a few seconds, and this glow plug gets really hot inside the combustion chamber in the cylinder, and so it'll cause an ignition of the diesel fuel, and the engine will start. And so the idea here was that the glow plug was in there, and it was left on all the time. And so if it flamed out, then it would relight itself just from this hot plug sitting in there. But it would make this real pop noise. And interestingly, Eastern Airlines used to fly these planes from Miami down to Buenos Aires, and they used to fly across the Gulf of Mexico, which is well known for ice crystal events. And they would say that typically they would hear the engine pop about 5 or 6 times during that crossing. Well, at least it kept going. For those of you who may be familiar with the Concorde aircraft, that was an engine we did. This is a jet engine, so there's no fan. It's just it's a single through. There's no bypass. We did that one. So the problem, and we'll talk a bit more of this in a moment, but the problem, of course, in these days, when Appendix C was being developed, it was developed for pure jet engines like this. So the conditions that they sort of chose that you should be required to test to were based on a jet performance, not a fan engine performance, which is causing some issues in certification processes now. So moving forward a few generations here, this is an example of an engine which is used on the Airbus A350. It's an RB or an XWB 84,000 pound thrust, and there's also a 97,000 pound thrust version. The fan is almost 10 feet in diameter, 118 inches. But interestingly enough, the first time we tested this engine, and this is in our facility in Thompson, Manitoba, which I'll show you a little later. We had an occasion where some glaze ice broke off, and we had 2 blades lose their tip. They cut the tip right off of them. And those tips went through and damaged 157 other blades inside the compressor. So that is a failure, complete and utter failure. So this is a $20 million engine. And I said, send the garbage bag. So anyway, so what they had to do, and actually, they actually admitted it, the Aviation Week, there's a story about this. So, and this is how engineering can get sidetracked, is that they had the same problem on the Trent 1000, which was the predecessor to it, and the Trent 900, and the Trent 800. And of course, the reason was they're trying to get the tip clearance down to nothing, right? To get them, you don't want any losses of air over the tip of the compressor blade. So they try to get that tip clearance down to 0. And of course, now when that ice gets jammed in there, blade gets bent, right? So they kept thinking, well, we got to make this. And so they couldn't pass. So they had to shorten the blade, stiffen it a little bit, give a little bit of room. Of course, you lose some performance to do that. And then each successive engine they designed went back to 0 tip clearance again. Yeah.
So would this be rim ice that's building up on the inside of the?
This was glaze ice.
Oh, it's
It's
glaze.
glaze ice because in this particular case, the engine has a heated inlet. So that splitter is heated. And so what happens there is that even though it's rime ice coming in, that heat from that's heating up there, it melts it, but it doesn't vaporize it. So the water actually runs back and gets behind the heated part, and there's no heat back there, and it refreezes. And when it refreezes as glaze ice, which is hard. I had an engine which goes into a commuter turboprop, which is flying all over the world. And in this case, they actually have heating pads on the inlet. It's like a mouse inlet turboprop, but there's all these heating pads that are controlled inside to keep it from icing up. Same problem. Ice melts, runs back, finds a place that's unheated, and it would start to build up a stalactite the size of your fist. And when they would do the throttle up at the end of the test, in would go this chunk of ice, completely trash the compressor. So we sent it back to them. Fortunately, the supplier was not too far away. Thing comes back rebuilt. They repositioned the heating pads, changed the heat cycle again. Same thing, poof, completely trashed it the second time, and a third time, and a fourth time. And the fifth time, not only did the compressor get trashed, but we had a simulated spinner on the front of the engine. It sucked that in too. So they raised the little white flag of surrender and went home, and they came back the next year and passed with flying colors. But the point is that, yeah, the problem is a little bit of heat is worse than no heat at all. You would like to be able, if you vaporize everything, then there's nothing to run back and refreeze. But of course, that takes a lot of power, and where's that power coming from? It's coming from the engine. So if you have to generate another 50 horsepower of electric power to power those heaters, that means 50 horsepower that's not used to push the aircraft forward. So that's a problem. Yeah.
For the XWB, how did they end up passing then? What design changes did they?
They shortened the blade slightly and they stiffened it. And so it gave a little bit more room for the ice to sort of squeeze through, and made the blade inherently a little bit stiffer. So they took a performance hit because of that. First stage is critical for being able to get air into the compressor, but they took that hit, and that's how they were able to pass. So this is an example of the geared turbofan that Pratt Whitney has. This is in the A220 or the old C-series aircraft, same facility. But this was actually the first of their geared fans that we tested. There's 3 different models used in several aircraft now flying. But there were some concerns because the geared fan, the fan is turning much slower. So there's now possibly more propensity for ice to accrete on it. And the problem is there's a gearbox inside the nose of the hub of that spinner, and that gearbox does not like to see any vibration whatsoever. So if there is vibration, those gears could fail as a result of it. So there was a lot of concern about the potential for vibration occurring in there. So let's look at some of the issues here. The problem, of course, and we'll get to this, but so when you're designing an engine today, what are you worried about? You want to increase the fuel efficiency. You want to reduce the noise. You want to reduce emissions. You want to reduce the weight or reduce the number of parts. You want to reduce the amount of bleed air that you might use to heat or warm parts of the engine to protect it. And you want to go to larger fan diameters and slower fan speeds because that gives you better propulsive efficiency. However,
something else that the airframer demands of the engine manufacturers, they don't want to pay anything for the technology.
yeah. You have to sell it for less.
Yeah.
Less is more.
Yeah.
But you see, the problem, of course, is that every single one of these designs, what you would do to design to meet those requirements is the exact opposite of what you would do if you want to design an engine which can survive any and all icing encounters. And of course, but no airline is going to, they don't, in the specifications for a plane that they want to buy, nowhere do they say, you know, design me one that will survive in any icing condition. They don't say that. They don't even care about that. They just want to save fuel, save money, so that they can make more money in service. And so that gets passed along. And at no time do the icing experts in the company have really any say in the design of the engine, but they are now the people that are stuck at the end after the engine's been designed and they're starting to do the development and certification testing. They're the ones who have to get it across the finish line and meet the requirements for certification. And if they don't, the aircraft cannot fly. The engine can't be sold. It can't go flying. And it goes back to the drawing board then to try to fix that problem. But it's very late in the game. Yes.
So were the old engines which were less efficient and louder, technically better at handling these icy conditions?
Yes. Well, yes and no. They were better from the standpoint that they had bigger stall margins. So if there was ice that was flashing the steam and pressurizing, they didn't care because their stall margin was this big. Now it's like that big. They also had a lot of residual heat. There was a lot of heat being lost in there, which kind of actually helped in some cases. Where they had trouble was the materials weren't as good. Like the materials weren't, I mean, they were the titanium blades and a lot of composites and things like that are much stronger. So the materials aspect has improved for modern engines, but the stall margins, that kind of thing have gone to nothing. So there just isn't any room for the engine to be able to swallow large amounts of ice rapidly. Which goes back to the time when I was talking about the older jets. They didn't have those issues. Now you have a big fan. If you look at the size of the core engine, the core that's driving that fan is very, very tiny. So the inlets are very small, and so engine ice blocking that doesn't take very long before exhaust temperatures start going up, because it's like a vacuum cleaner. You start choking off the inlet, it starts speeding up, and there's no air coming in to keep things cool. So you're going to burn the back end out of the engine. So those are problems which modern day people are having to deal with. But as I say, it's not really discussed during the initial design phases of the program.
Well,
oh, okay, Greg, you can disagree with me, but
yeah, I think
you're in Phoenix, for God's sake. They don't have any ice out there except in the glass.
Yeah. Well, I think it's probably fair to say each engine company goes through cycles on their design capabilities, whether it be icing or aerodynamics or structures and so forth. And I can speak to when I worked on the conceptual and development and detailed design of the AS900, commonly known as the HTF 7500 or 7250, whatever commercial name you want to use, that there was, let's say, attention brought to the issue of icing. And some of that came from the first application, Bombardier, where they had, let's say, poor experience, and they provided, let's say, some persuasive arguments for Honeywell to be working on the matter. And but you know that Honeywell, of course, it's 20 years plus since that design, and there's been change in personnel and so forth. So it probably wouldn't necessarily go the same way.
Well, we've seen other engine manufacturers where the same problem comes up again, and a
Yes.
generation later comes up because the information never got passed down, especially when there was a transition from everything done with paper to everything designed on computer. All the design practices that they had in paper didn't make it into their computerized design practices in some cases. So
Yeah, so
Yeah.
there's been a lot of design knowledge lost.
yes,
And the I don't want to say, there's a politically correct way of saying this, but generally upper management, particularly if they're remote from the facility doing the work, just sees those endeavors as an expense.
Yep.
And so they seem to be okay with the thought that going through and relearning it at some future date is okay, perhaps because it's not going to happen on their watch.
yeah, hopefully. Okay.
Yeah.
Thank you, Greg. All right, so here's an example. This is what the front end of the XWB looks like. And you can see it's obviously a very, very large. But the difference here, the interest of note, is that on the older generation engines, the fan blades were relatively straight. And so the fan is a really good catcher of ice, right? Because it's out there, it's the first thing the cloud sees. And so there's lots of surface area for it to build on. But in the older engines, that straight blade kind of went right to the hub here. And so it tends to block the core, give some protection to the core of the engine. But you can see here now, you can see right through the fan blade here, because at the hub and the lower end of the blade here, there's no curvature to the blade hardly at all. So there are gaps here, and the cloud goes through here and actually then gets into the core. The cloud on the other part obviously hits the big paddles, gets taken out of the equation, not a problem. And when that ice sheds, it goes down the bypass duct and out through the back and never bothers anything. But ice that makes it past this point here in the core now builds up on the splitter, on the inlet guide vanes, and first rotor, and sometimes first stator. And that's where the problem lies, is now you have all that ice sitting there in the inlet of the core. And when they are at the end of each test, the last thing you do is they have to slam the throttle to 100% takeoff power. And the engine has to be able to get there in about 5 seconds. And there can be no loss of power or damage as a result of that event. So they're simulating, essentially, you've come out of a cloud and the pilot has to maybe make an abrupt maneuver or something like that, has to climb quickly. So they need to have all the power the engine can get. They have to show that they can deliver 100% power in a timely fashion. And the engine doesn't stall or vibrate excessively or do everything like that. So, yes.
Just from this photo, I was thinking, do you guys ever have any concerns about ice building up on the outside of the core and then like potentially like interfering with any of the equipment or stuff that's mounted outside of the core?
Outside of the cell, you mean? Or
No,
outside
no,
in the fan
like,
bypass? There's nothing in the fan bypass that's of any now. Yeah, some cases there may be inlets for oil coolers and things like that out there, which could be an issue. That's
yeah.
right. Greg, you have a
Well, some other engines that have EPR type or integrated EPR type controls, they have to be where they have a pressure measurement in the bypass duct.
yeah.
They have to be thoughtful about protecting that instrumentation from
Yes.
ice damage,
Yes.
because it can affect how the engine is how it's controlled, if you will, what schedule it's going to set for power.
Mhm. Yep, that's true.
And for military engines, there can be also concerns about getting to the afterburner ring, you know, where the fuel is injected.
Yeah.
You know, even if it has a low probability, one still needs to look at it.
Sure. Oh, yeah, definitely. Okay, so another example, moving to future designs, obviously, this is an example here of the UltraFan engine, which Rolls-Royce has started testing this year. And it's a 140-inch fan, which is the largest engine in the world. And it has composite fiber fan blades, and so it's a 12-to-1, I think it is, bypass ratio on this thing, on this monster. So it is a very large. So, but if you look again at the fan blade, you can see that at the hub, there's essentially no curvature. So the cloud is essentially going can go sort of right on by, and can then get into the core itself, whereas obviously the cloud on the other part is going to be taken out significantly by the projected area there. But it really sort of exposes the core to a significant amount, potentially a significant amount of ice. And even other future designs looking at these unducted fans. Here's an example where the fan is at the back, counter-rotating fan. The core now is completely exposed. There's nothing in front of the core to take out any ice. So in this case, the core is seeing all of the cloud, not just part of it. So it's completely exposed to the threat. And you now have to look at how do you protect it without consuming large amounts of power and so on to do that. The fan, and then the other issue you have, of course, is that the fan is now going to shed ice. Normally there's a casing around the fan, so ice that sheds off hits the casing and then gets directed out the bypass duct. Here, when the ice comes off of these blades, the blades that are passing by the fuselage, they're going to get hammered by ice, hard ice shedding off and hitting the fuselage or the wing or whatever the case may be. So that is something they now may have to start putting armor protection on the fuselage to protect it from that impact. So some of the future designs of aircraft, we see these very, very large diameter fans, which are now have to be mounted up on top because you can't put them under the wing because they'll be dragging on the ground. So again, big diameters can result in some significant issues. Large amounts of ice are going to be coming into those. Or you get case where you have here where in this V flying wing for the design, where the air engines are now buried into the fuselage. So you may have issues with ice accretion in the inlets, potentially causing blockage and distortion, which will affect the performance of the engine to some extent, and the possibility of ice shedding off of the front part of the fuselage and getting sucked into the engine, coming in around the surface. So there may be larger possibility of impact damage from ice slabs. So let's talk a little bit about the facilities that are around the world for testing icing for engines. There are several sea level facilities. Currently the largest one is in Peebles, Ohio, but it's now been mothballed. It's not in operation anymore. The climate change has resulted in not being cold enough for them to run tests there all year on a repeatable basis. There is the GE facility in Winnipeg, which is in the Winnipeg airport, which is strictly used for GE engines. It can do 4,400 pounds a second of air flow through its facility. It's what's called a free jet facility. We'll have some pictures here. The Glacier facility, which is owned by Pratt Whitney and Rolls-Royce, and NRC operates the spray system for them. It's currently operating at up to 3,500 pounds, but we're upsizing it to 5,000 pounds. So it will become the largest operating facility in the world in 2025. And M7 here in Ottawa, where I am located, does basically business jet size, regional jet size engines at about 800 pounds a second. We live in a refrigerator here in the winter, so we rely on free cold air, which is why the facilities are all located in Canada. So interestingly enough, 80% of all engine icing certification is done in Canada. 100% of all large engine icing is done in Canada. In fact, 100% of large engine icing is done in Manitoba, because the 3 engine manufacturers all have their facility either in Winnipeg or Thompson, Manitoba. Otherwise, Manitoba has no redeeming features whatsoever. Anybody here from Manitoba?
Yeah.
Just
Let
me,
me
Jim.
repeat what I just said.
Just me, Jim. Jordan.
No, the people were great, but we've never been to Manitoba.
People are great.
The people are great, but that's about it. So there are some sea level refrigerated facilities, and one is McKinley in Florida. They had a fire a few years ago, and their capacity has been reduced somewhat, but it is a humongous hangar. You can put a C-5 Galaxy aircraft in this hangar and chill the air temperature down to minus 60 or so. But you can also warm it up to 150. They can do hot and cold, and they can do icing as well. And then there's the RTA in Vienna, which is a closed loop. I was there back in June. This is a cool facility. It's the European Union paid a lot of money to help build it. And they actually have 2 closed loop icing or wind tunnels which can do icing, and they can control the temperature so they can run in July at minus 40. But they basically do small like model testing. They were originally built to do trains. So the test section is 300 feet long or 100 meters long. They were doing train cars. They do subway cars. So Alstom is one of their biggest customers for subway cars. And they can do helicopters and small jets. And then there's the altitude facility. So there's a ADC, which is a U.S. Air Force facility in Tennessee. It is the largest of them in the world. It can do 1,600 pounds a second. It costs $100,000, it's actually probably about $150,000 an hour to run it. And so a test there will cost you in the $10 to $15 million. Whereas in the sea level facilities, you're talking maybe $2 to $3 million. And most of that is electricity to be able to run all of the compressors and exhausters and refrigeration systems. CM in Russia has a very old and very rusty facility, so you get a decent cloud, but it's a fair bit of iron rust floating around in your engine as well. The DGA in France is another military facility, and they generally do, again, smaller engines, business jet engines, and shaft engines. NASA in Glen, which is in Cleveland, has an altitude facility which is set up for ice crystals specifically, and but it is also used heavily by the military, so it's very difficult to get into it. And NRC has a facility which is affectionately referred to as the Rat Pack. There's no rats in there, trust me. But it's a research altitude ice test facility, and we can simulate up to 50,000 feet, and we do ice crystal testing in there, which is the pictures that I showed you earlier were from that facility.
Wait, for Rat Pack, you guys actually, is it depressurized? Like,
Yes.
Okay.
So you suck the air out, you reduce the pressure inside. It's a big pressure vessel, which the engine sits in. And so you can simulate the pressure, temperature of whatever altitude you're looking for. We can go down to -65. Actually, today they were at -72 for a particular test, but yeah, we're actually upsizing it, so we're going to double its capacity. 10 pounds a second is so small we can just do turbo shafts or APUs, that sort of thing, but or rigs, test rigs. We're doubling it to 20 pounds here next year. So there's some pictures of icing testing done in one of our icing wind tunnels. This was a Sikorsky setup. The engine is actually inside here. And so this is the upper half of the helicopter that they gave us the model of. And here's our icing facility that used to be out at the airport in Uplands, and there were steam injection nozzles. You can see the helicopter hovering in the cloud, so you have to have pretty good size to be able to fly in zero or no visibility that close to the ground. We actually had one helicopter crash, not crash, it was a hard landing. But the pilot broke his back. He survived, but yeah, that's not fun. This is the McKinley facility in Florida. So you can see it's a very large hangar. They can bring the plane in, and they have a portable spray system which they can run it in different configurations depending on what speed you want. In this case, they're actually blowing the cloud at the engine while it's running. So they have fans that are blowing the cloud at it. So that's referred to as free jet capability. And then here's the ADC altitude chamber where they can run in either free jet, where the engine is disconnected and you blow the cloud at it, or in direct connect, where the tunnel or the chamber is connected directly to the engine, and all of the cloud is going to the engine, none of it's going around the engine. There are advantages and disadvantages to each of those. This is the GE facility in Winnipeg, which was built by NRC in Mirabel, and then the whole thing was trucked to Winnipeg and rebuilt. And this is a free jet facility, so you can see there were 7 fans, and then the spray mast is located behind it, and the cloud is then blown at the engine while it's running. They had to upsize the facility, added 4 more fans to be able to accommodate the big GE9X, which is on the 777X, which is now flying. It is currently the largest engine in the world. So now the UltraFan is running, it's not flying. It is 4 inches larger in diameter. And this is the Glacier facility in Thompson, Manitoba. So it's a 25-foot diameter inlet, 512 nozzles. It is a direct connect facility. It can handle engines up to 150,000 pounds of thrust, and that's where Jack, sitting up in the back there in the middle, spent 16 months of his life in that facility.
I think sledding and fishing are redeeming qualities for Manitoba.
Yeah. He survived. So what are the challenges here for engine design for icing certification? Well, obviously, trying to reduce the accretion of ice onto the metal parts is a big one. And there's a lot of work being done in trying to come up with either coatings or materials which are ice phobic. So the ice just doesn't stick to them as well. The problem with most of the ice phobic coatings is that they don't stay on very long. They get eroded off. So aircraft are flying, the air is often very dirty, right? There's dust and there's ash and there's all kinds of things up there. And so those coatings tend to just get eroded off due to abrasion. And so they're not there for very long. And so they end up not protecting you when you need them. And so there's a lot of work in nanotubes and that sort of thing now, trying to make base materials which may have isophobic properties, but still have the strength that is needed to be able to take an impact or a bird or whatever, ice slab. The other option is to try to shield the core inlet of the engine from direct ice or ice cloud hitting it. Some have tried to sort of hide the compressor core a little bit far deeper in, but that's not an easy thing to do in some cases because you then have more distortion, and then that creates issues with the operability of the compressor. You can make the compressor blades out of stronger material, but you still have the problem of ice being incompressible. If there's no gap, then even the hardest materials are going to bend or break. So you have to have something there, but at least if there is some room, then you don't have to worry about blades breaking off completely. And then the other option is to come up with ways of improving the stability of the compressor. So even if the ice does go in and it does flash the steam and it does cause a pressure pulse, the compressor is stable enough and the combustor is stable enough that it can withstand that pulse. It's very short duration. If it can get through that little blip, then it won't surge and it won't flame out. So, but that's, as I said, the move is always to make that surge margin as small as possible now to get the maximum amount of energy power out of that core to drive that big fan. So time will tell as to whether maybe you people here will be the ones who come up with the breakthrough technologies to improve that stability of the compressor. So, in summary, then there are icing is a major challenge. Every engine that is going to be designed to go on to an aircraft, a new aircraft, has to pass its certification before it's given a type certificate to allow it to fly in icing conditions, which means any cloud that it might go through. And so it is one of the toughest tests the engine has to go through. And as I said, having done this for 40 years, I've seen recently engines failing because of the fact that they just don't have that stall margin, and they can't handle that. So it ends up having to be redesigned. They either have to slow down the acceleration to give it a little bit extra time, or change some of the design of the mechanical hardware, which that takes it. You've lost a year, especially because you can only do these tests here in the wintertime. If you fail one winter, you have to wait till the next winter because you're not going to be able to redesign it and go through it. Because if you change something, you're going to have to do other tests too to verify it. You're not going to get it back into the next until a year later. So you've lost a whole year. And if you lose a year in delivering your engine to the airframe manufacturer, the lawyers are going to be all over it. And it's going to cost you millions of dollars in penalties. So it's still a difficult test to pass, and having done 2 engines last year, both of them sustained damage. Each one $12 million. They sustained damage and had to be redone. So I sometimes my inner voice is going, yes. The ice wins. But the other side, I always feel sorry for the engineers that are standing there, their long faces, and they're like, oh God. And I did once for a Japanese company, and it was for a helicopter, and they had to survive 30 minutes of icing, inadvertent icing, and after 5 minutes, it was all choked up, and the oil cooler was completely plugged, and it wasn't going to work. And before they started, I said, "So, what's your plan B?" I looked at the configuration. This is not going to work. But nobody asked me. And so I said, what's your plan B? Do you have an alternate configuration that we can run? No, this is all going to work. Okay. So 5 minutes in, that was it, over and done with. And so, the engineers that were there, they were young. I mean, they were fresh, very fresh. And I thought they had to sit on the phone and talk to their very senior managers back in Tokyo, or not in Japan, and explain that they had just failed the test after 5 minutes. I thought they were going to take out the sword, and they were scared to death. I think they were scared of what their boss was going to do. But anyway, we ended up coming up with a solution that would work, and it was fine. Yeah, they were completely, I've never seen anybody with so sad looking in my life. But they had to explain that. So, yeah, if you go to Thompson, I suggest you rent the Avis or Dogs sled. That's the best way. Don't go with the budget or Hertz. Their dogs are not as good.
You get your
Yeah. I will, let me just, here.
Thanks, Jim.
You're welcome. Let me just play.
For Chad, and actually,
Let me just, let's see if we can. Okay. This is the glacier facility in Thompson. That is the old part. Give you some perspective on how large it is, and you see how big we are compared to the size of the inlet. Okay. Any other questions? You have all the questions.
Probably go first.
Whatever.
Yeah.
Go ahead.
Well, I just wanted to ask, because you mentioned that so many engines recently have been failing, their icing certification tests due to such slim margins. Do you think that there should be stricter regulations or even tougher testing on, the current generation of engines to ensure that they can handle the icing conditions that they face?
No, because obviously they're struggling, and they making them any tougher. It could be nothing. So the airworthiness people like to follow historical trends. So these tests have remained the same for decades for the very reason that they want to see that there's no divergence or whatever. So they're testing to the same requirements. Therefore, because if you change the rules and then suddenly the failures go up or go down, I would say, yeah, it's making it tougher isn't the solution. I think that the solution is to try to integrate earlier on in the design inputs that might help guarantee that they do pass, as opposed to, like I say, there's so much focus on the improvements in efficiency and all that sort of thing. But they don't have as much focus as they should, I believe, on some of what they could be doing in icing to try to improve those characteristics, and therefore it'll save them time in the end because they don't fail the first time. They can get through it on the first try.
Thank you.
Jim, my recollection of, this is a couple decades ago, is that when we were doing some of the ice tests at your facility, that it was in a test cell that wasn't capable of measuring thrust, or maybe it wasn't accurate. Can't remember. Is that?
No, it was. You guys chose not to.
Was that it? Okay.
Yep.
Yeah. Yeah. Okay.
All of our icing test cells can measure thrust.
Yeah, it was because we ended up coming up with an alternate method to calculate it.
Yeah, you put probes in the bypass duct, which we had to put in and take out when we were icing and put back in again while the engine was running, I might add.
Yeah.
But yeah, no, the capability was there, but for a reason that I can't remember you decided not to go with that option, but
Yeah, I think that, yeah. It's old history.
we're both
Uh,
old, Greg. But by the way, Greg and I were graduate students together here at Carleton, like I say, 100 and some years ago. We were in the same office for a while. I mean, I spent most of my time at NRC, but he was stuck in the office, in the office here at Carleton. But yeah, we've talked a number of times over there, but we haven't seen each other for a very long time. So he gets to live in a nice warm place. We get to live here.
Well, yeah,
I wouldn't want to live at 120 degrees Fahrenheit. You could keep
yeah, this summer, I think we had close to between 50 and 60 days of 110 degree temperature or warmer is a set number of records.
like living
But-
in an. Anyway.
Yeah, sorry, go ahead.
We have another question here from the audience here. Go ahead.
I guess Greg could answer this, but earlier you said that the number of fan blades has been going down. Is that due to efficiency or is that just due to cost?
Well, again, you're trying to reduce the weight. And so we now have fewer blades, but they're much wider blades, much wider span on them. And so that's the efficiency improvements in these weird shapes of blades have allowed them to reduce the number of them, and they're turning much slower as a result of that. So all of that has improved the efficiency of them. That the pressure rise across them and that sort of is significantly higher than it was 30 years ago. But as I say, has created other issues as a result. So at the back, yeah.
First of all, thank you for the presentation. It was great. So real quick, you said like when you were testing the engine for like the blue from the fan, you said you're looking at it and like you didn't think that it was gonna work. Like what gave it away?
They had protective screens on the inlet for the core and also for the oil cooler, and the openings were just way too small. Ice loves screens. Screen is the most efficient ice accretor you can come across because a very large surface area for the volume. So it ends up building up ice very easily, and there just wasn't enough open area, and it just grew very quickly and completely blocked the flow. So, and I looked at it and said, well, that's your only option. You shouldn't. Normally people show up with 2 or 3 things and they'll sort of, let's start with this one. We think this is our best. And then we have this one and this one. And they had 1. So I said, okay, this might be a very short test.
That reminds me of a 777, like I think it was 15 or 20 years ago, where ice crystals built up on the oil filter.
Yeah.
And that caused a dual engine flame out right
It
before.
crashed at Heathrow Airport.
Heathrow,
Yeah. But that's ice crystals in the fuel.
Yeah.
At the back.
How many times does an engine pass? Is it just once?
Once. Now, if the engine, so we've done examples where a few years down the road, they make some design changes to the engine, which if those changes are critical to they're at the front end where maybe fan blade change or first stage rotor core or the splitter is changed in some way, that would perhaps result in different performance in icing conditions, they have to recertify that. So that is the decision that's made between the engine manufacturer and the airworthiness people to see whether or not they have to go through a full test. Some cases they may be able to get away with just an analysis to show that this is not going to seriously change the results at all. Sometimes if they do, if the engine manufacturer is going to do multiple versions of the same engine, they may test the most powerful version first. And if that's okay, then they can do smaller versions of the engine and not have to necessarily do a retest on the smaller versions, but not the other way around. If you do a smaller one, a lower thrust one, and you want to upsize it, you won't be able to get away with, but you'll have to do some test. May not be a full, but you'll have to test a certain amount of it. So we got one here.
Yeah.
Go ahead.
Hey, if I can just jump in, Jim, Omer, I'm here in Houston. First, shout out to my MDS colleagues who have joined, Jordan, Chris, Kiana, Oleg. Might have missed one or two. But there's a question in the Q&A here from Si Hong Yang, actually two questions. First one, crystal icing facilities are cost prohibitive for university labs, especially with real turbofan engines. How can university labs further contribute to crystal icing in addition to modeling efforts? So that was the first one. And then number two, a certain engine received FAA airworthiness directive back in 2016 because of engine icing issues, and the solution is to open a window at the IP compressor stage. How reliable is this solution, and are there any other promising concepts? So those are the two questions from Si Hong Yang.
Okay, well, yeah, it is very expensive to try to build test facilities for universities. You have to have coal generating equipment, which as we see is expensive. And you have to have some sort of wind tunnel. Now, NRC has some facilities, and we're always interested in perhaps working with some universities to develop they could sort of be part of our tests and use some of that data to further the modeling aspects. I think most engine manufacturers have decided that the modeling is the way to go, but they need to build up enough confidence in those models through rig testing, component testing, to be able to show the airworthiness people that their model works over a wide range of capabilities, and that they can extrapolate to the full-blown situation, and still those results would carry over. And so that they're nowhere near that now, but they're working towards it. And I know GE unfortunately, they're using a university in Bangalore to do all their simulation. So I would suggest that there are perhaps opportunities for universities in Canada to sort of get on board. But that's certainly an aspect. But trying to build their own facilities. Now, what universities could do is maybe come up with some concepts for what rig might be tested in an NRC facility. So there are some rigs which you could come up with some specialized instrumentation for, to be able to help quantify the extent of the ice accretion, the density of the ice, the ratio of ice to water, those types of things. And new instrumentation there's some openings there for improvements, which universities could probably help in. On the second question, yes. So there's one of the engine manufacturers had a real problem with ice crystal encounters, to the point where they were not allowed to fly within 100 nautical miles of a thunderstorm. And so that is severely limiting. And so what they did, one of the concept they came up with, there are essentially bleed doors between the LP compressor and the HP compressor. There's a duct called the swan neck duct, and they were able to put these essentially doors which would they would pop open to allow the ice crystals to be centrifuged out into the bypass duct and not go all the way through. That helped, and it can work. The only problem is that when you do that, you lose performance. You're bleeding air out of the compressor of the engine, and it's now not going through the HP compressor and everything, which is where the real work is done. And so there is a performance hit because of that. The problem is that you now have to have a system, an infallible system, which tells you when you're in ice crystals to know when it's time to open the doors, and only keep them open long enough until the threat is over, and then close them back up again, so that you're not wasting all that valuable air. So that gets into detection and fail-safe detection modes, better instrumentation, which means more weight, more complexity of the aircraft. Aircraft manufacturers are loath. We had guys, they were trying to get, it was on a helicopter, they were trying to remove 1 pound. They wanted to remove this the speed sensor off of an IPS blower, which was going to save them 1 pound. And they spent a lot of money trying to get rid of that 1 pound. So every pound, every kilogram of weight that is on there is crucial. And they are, even though the thing may weigh 700,000 pounds, they're very reluctant to add more instrumentation or equipment to be able to do that. So if you can, coming up with schemes which would allow you to detect it without adding any more weight, or using, I know Boeing has come up with a scheme where they're actually looking at some of the basic engine parameters to try to see if they can tell when the engine is actually ingesting ice. When there is ice so there's a slight change in mass flow coming through the engine because of the presence of cloud or ice crystals. So they were looking at parameters which are already being measured in the engine to see if they could detect very minute changes in the performance of the engines to be able to give them the hint that there was some ingestion of ice in one form or another coming in. But yeah, that's always the dilemma. Yeah, you can come up with all kinds of cool things to add, but if it's going to add weight, you're going to need more power to run this equipment. That falls in the nope, don't want that.
So Jim, can I add just a few thoughts to that? You very good, but just I can add a few other things from my own experience that might be useful. So with respect to weight, right, roughly for every kilogram of weight that is of the engine, you have to have order of magnitude 3 pounds of structure to carry it. So the influence of weight is very concerning to the airframer, because if the weight goes up beyond what's allotted to the engine, then they're looking at having to not put on as much fuel, or they have to reduce payload, passengers, luggage, all that kind of thing. So it has a strong domino effect or influence on the aircraft.
Yep.
With respect to bleeding behind the LP or IP compressor, one of the other side benefits of that is it improves operability margin on that particular compressor.
Yep.
But on the downside of that is it takes away operability margin on the next compressor. It causes the op line on that compressor to move up towards surge. So it's always those sort of trades are very tricky for the engine manufacturer to be doing.
For every solution, there's another problem.
Exactly. And then back to the thought about what universities could do in terms of facilities. And this is moving away from engines a little bit, but it's just to illustrate an idea of how challenging some of this problem is. So, I worked on the last bit of my career, mostly mid-size biz jets with wingspans of order 40 to 50 feet. And those kinds of airplanes relative to, say, a 727 or those kind of commercial airplanes, where the wingspan is much larger, those airplanes, larger airplanes, have bigger leading edges compared to the business jet.
Yep.
Yet the ice particles are the same size. They don't scale with the aircraft, right?
Nope.
It's just the environment. And the smaller airplanes are quite a bit more sensitive to ice buildup on the wings. So they can't take as much of a thick layer on the wing relative to a large airplane before they start losing stall characteristics. And consequently, the anti-ice systems on small airplanes are very demanding. So on the airplanes like the G280, the Challenger 300, longitude, Cessna longitude, these kinds of airplanes, they use as much air coming out of the engine as they do on a 727 to anti-ice the wing.
Yep.
So this is very challenging for smaller engines because they're taking a larger percentage of the air out of the machine.
Yep.
So, perhaps there's some opportunity in the university area to better understand ice capture and how to deal with that on aircraft wings, and that will have a benefit to the engine in a more indirect manner.
Now, if you can make the icing system on the aircraft more efficient, needs less energy from the engine, then that helps the engine. So
Yeah, I guess we have, a few
We
questions.
have a couple more
one
questions here in the audience. Here.
What's like typical duration, start to finish for this test? So maybe like a very quick one, like you said, 5 minutes for the runtime.
Some tests, about the shortest icing test we do, like typically there's about 30 to 40 icing tests done as part of the certification. The shortest duration is about 5 to 10 minute range, generally high intensity. And then the longer ones can go for 1 hour or 2 hours. As I said, I did one that was over 3 hours, but the longest ones are usually what we call the ground fog. So you're simulating the aircraft taxiing on the ground for, in one case, an hour or 2 hours. And then the problem with that's actually a very tough test because now the engine's turning very slowly. So there's no ice being shed off of it. It's accumulating. It's a very low concentration, but if you accumulate it for an hour, the core has that ice that's just building up and building up. None of it's being shed. And they get to the end of the runway and the pilot then has to hit the throttle, the full power. All that ice is suddenly going to go whoosh into that core, and that can end up being a problem. It got worse because in the old days, they used to only test ground fog down to -9 Celsius because that's mostly where it occurs. But in 2 places in the world, Oslo, Norway, and Denver, which is high, they can get ground fog down to -18. And so they had a number of incidents out of those 2 airports where several planes in a row took off, and each one of them had major damage done to it during takeoff. So now they require icing ground fog to be tested down to -17 or 18 degrees. Yes.
So you talk about Appendix C, and then you mentioned just the numbers, right? So 20 to 70 micron diameter.
Mhm.
A lot of the research in the last 15 years is just talking about super cool large droplets.
Yeah.
So you didn't mention anything in relation to that. How is that coming into engine icing?
So so it's Appendix O, which is the super cool large droplets. Generally, that's now freezing drizzle and freezing rain. It is something that the engine manufacturer has to look at, but it turns out that the engine really isn't bothered by that at all. The wings are. The wing is the problem for Appendix O. And the reason, of course, is the bigger droplets, they actually hit the leading edge of the wing and they flow over the wing and they'll actually get past the de-icing system and start building up a ridge along the wing behind the heater or the boot. And so there's a very sad example of an ATR 72 that crashed in Indiana, where that exactly happened, and everybody was killed because the plane just stalled and augured into the ground. But it's so for wings, empennage, tails, the super cool large droplet is a serious problem, and they have to do a lot of testing. The problem is it's very difficult to replicate those conditions in an icing wind tunnel. Because the larger the droplets, the more their gravity. Mother Nature has the advantage of time. It's making those big droplets, and it takes hours to make them, and there's lots of time to make them and keep them suspended in the air. But when you're spraying them out of a nozzle, which is maybe 20 meters or 10 meters away from the test article, there's not enough time those droplets to sort of stay. They literally will be falling out of suspension unless you had a vertical tunnel, you could drop them vertically, but they will literally end up, most of them on the ground. Because in the air, they're static. It's the plane that's moving. The droplets are just sitting there floating. But when you have to now blow them at something or in a tunnel, they generally tend to sort of just fall out of the cloud and land on the floor. So it's very difficult to get a uniform distribution.
And I guess that's
Hey,
another-
thanks, Jim, for the answer. I have a question from someone you might know, Jordan Illot, who's
Well,
the
don't know him.
manager.
No, don't know
Never
him.
heard of him before. He's the
never.
manager of the MDS operated glacier facility in Manitoba.
Okay.
Oh, might ring a bell. But anyway, so he's asking, you showed the GE and the glacier facilities. One is a direct connect and the other is not. Why would one method be preferred over the other? So feel free to answer as you.
It's just historically been that way. GE, for example, always does theirs in free jet, and the rest of the world, or majority of them, do it in a direct connect. The direct connect is cheaper because you don't have to have big fans which are blowing the cloud. You also have to have the full nacelle mounted on the engine, and you have to heat that nacelle to prevent ice from building up and breaking off and getting sucked into the engine. So that's an additional problem. The other problem with free jets is that at the higher powers, the cloud tends to get pulled inward toward the center because it's pulling from even behind the engine. So it's coming around the inlet and it's displacing the cloud coming in, and it pushes more of the cloud toward the core. The direct connect is cheaper, as I mentioned, because they don't have the fans and you don't have to have a nacelle. Some would argue that the uniformity isn't quite as good at the outer edges, tips of the fan, but I think that is because that's not where the action occurs. The worst of icing is in the core, in the center, not toward the tips of the fan blades. So if for some reason or other the distribution is lesser out there, then it's not a big issue. Now, so you can tell by my bias that I prefer the direct connect. We do both at NRC. We actually do another mode, which is called bypass, where we build a tunnel around the engine, put the nacelle on it, and we then suck on the back of the tunnel with another ejector system, so we can actually simulate forward flight. And that is actually the most representative of what the engine is actually seeing in flying conditions. But we can't do that. We can only do that for very small engines. ADC can do it for some larger engines, but that it takes massive amount of power to be able to do that.
Okay. Hey, thanks, Jim. Appreciate the answer.
No, how come none of the old guys in the room are asking any questions? That's only the what up, guys? Come on, yeah, Manfred, say something.
There's a lot of activity now in new fuels, SAF fuels and hydrogen and all that stuff. And you mentioned the stability of the hot section, the combustor, the stall. Is there any implications there on getting new fuels and your issues on icing?
Well, yeah, to that point, if the stability of the combustor is less as a result of these more exotic types of fuels, synthetic fuels or pure hydrogen, then the risk is that a large amount of ice coming in is going to take out that flame, which might have survived in a stable combustor. If it's any less stable than it already is, then that means a greater opportunity for a flame out. Somebody asked, I've been asked the question, well, now we're moving toward electric motors. You know, does that mean that icing is not a problem anymore? Well, no, it still is, because electric motors produce heat and you have to cool it. So you have to have a cooling system to cool that electric motor. And to cool that, you need air. And anytime you bring air in to cool something, you're bringing in the cloud with that air. So now you have the possibility of ice accreting in that cooling system, that whether it's a heat exchanger or whatever you're using, it can then get blocked up with ice, and if it blocks up, then you don't have any cooling anymore. And now your engine overheats and melts the core out of it, and then now you're going down again. So for every solution, there is another problem. So anytime heat is still a problem, no matter, unless you're using dilithium crystals and warp drive, there's heat, and that heat has to be dissipated, and you unfortunately are using the air. That's the only cooling medium you have out there is air, and that air has moisture in it, and that moisture is going to then potentially freeze. And now you have to make sure that the inlet to the heater, to the heat exchanger, is now heated or protected somehow to keep that ice from accreting. So yeah, but the beauty is that Mother Nature guarantees me a career for as long as I want, because you can come up with anything you want. Aside from the dilithium crystals, there's nothing you can do out there to get around the fact that you have to fly through a cloud, and all those clouds are, any cloud is a potential ice producer on an aircraft. So
Can I just add to that, Jim? I have some recent experience because I'm doing some consulting work for some people trying to.
You're supposed to be retired, Greg.
Yeah. Well, I failed. So been doing some consulting work for some people trying to replace gas turbine turbofans with electric drive fans. And of course, on a lot of the gas turbine nacelles, the leading edge is anti-iced with hot bleed air from the engine.
Yep.
That's one of the benefits of having a compressor section, is you get that free, if you will, hot air.
It's not free.
And,
it's not free. Very expensive.
Well,
Coming out of the compressor, back of the compressor, it's very expensive air.
I use the free quote unquote, but there's no immediate light source with an electric drive system.
Yeah.
And so
well, that's the problem with all these vertical lift drone type things. They don't have any hot air on them to be able to anti-ice wings or rotors or anything, because they're all electric. So there's no, that's the problem with flying these drones, or these new air taxis they're talking about, being able to hop from A to B. There's nothing to de-ice or ice protect them with. So that's why they're looking at ice phobic materials and some of these other novel things to stop the ice from building in the first place. But there is no heat source available on an electric aircraft or electric motor.
Yes, agreed. And then some of these arrangements to deal with that problem, they start driving small compressors on aircraft to provide the bleed air that they need. And of course, they have to have some system anyways to provide cabin pressurization and fresh air to the passengers. So it as you said before, it's trade-offs.
We have another.
Yeah, one more
one more
question in the room
question from
before,
the audience here, and then
So if you can speak to the repeatability of aircraft engine icing testing. I come from the perspective of icing on wing surfaces, where you're looking at designing the surface. So you're dealing with single droplet, which is not repeatable at all. Engine icing testing, much larger scale. So could you talk to the repeatability?
So here's the funny thing. The airworthiness authorities only require you to pass the test once. And that seems to be the way people, I only had one, and it was the Japanese guys who asked that I repeat the test 3 times to show that how repeatable it was. And it was actually very repeatable. And I must admit, I have seen cases where it is, but there is some probabilistic nature to it, especially not so much with the accretion, it's the shedding. That's where the variability comes in. And so so that results in different vibrations. So you might be able to show that you have the same loss of thrust or whatever, but it's very hard to predict what the vibration signature will be, because the variability in the probabilistic nature of the shedding characteristics. I had one engine where we had an asymmetric shed. Half of the fan shed all at once. Half, exactly half. Like a lot of times it's a blade here and a blade there, but this one, poof, this whole side went and the other side was there. So you had a massive imbalance. You want to see some people jump out of their seats. It was very exciting. They'd never seen this in their life, and they didn't. Some of them didn't think it was possible, but I said, no problem, I can do that. Anyway,
Tear itself apart.
the vibration shot up very rapidly, faster than anybody could move. But but other than that, the accretion rates are very consistent. But I've often thought, you know, is it possible that on some of these tests that they just squeaked by? They were just on the edge and they passed. And if you ran it again, where they were just on the other side, that they would have failed. But the airworthiness, they basically, the engine manufacturer, they get the test, pass, test, check the box, move on to the next point. So
That's very true of the bird shot tests and all that kind of thing as well.
yeah, well, yeah, exactly. Anything where you whether it's hail, whether it's rain, or any of those, you think, well, if I do that a second time, was there an element of luck? I had one old geezer from a company I won't mention. It's not you, Greg, who basically referred to icing as the roll of the dice. You know, maybe this time you're lucky, and another time you aren't. But I think he was being a little pessimistic. I've certainly, and I think Jack will attest to having seen a lot of that when we were run the same test another day. Yeah, okay, that looks very similar. In fact, on the ground fog test, you get no shedding on the big engine, the big diameter fans. You get no shedding off of the tip of the fan blade for about 22.5 minutes. You almost set your watch by when the first shed was going to occur, and it was somewhere between 22 and 23 minutes that it would happen. So, I mean, to me, that speaks pretty good, that the repeatability is pretty good. But I've had some people where it's like, geez, you know, that test could have been just on the fuzzy edge of a pass.
Well, your repeatability is within like 5%. It's not at like.
Oh yeah. Well, see, that's the thing, you know, if you look at the uncertainty in pressure measurement, for example, is a good one. Certainly in pressure measurement, it's like a tenth or less of a percent. The uncertainty in the droplet measurement business is 20%, plus or minus 20%. In the concentration, it's at least 10%, sometimes more. So it's a different realm in terms of there's a much bigger uncertainty in the measurement of these trends. So to me, that is something that universities could work on, is coming up with ways of being able to make it more accurate, less uncertain in the measurement of these parameters like droplet size and liquid water content, for example, or total water content in the case of ice crystals. That's where there's a lot of work that could be done to bring those uncertainties down into the 1% or better type of thing. So that's something definitely a university could contribute significantly to. So that gets into optics and all kinds of things too, which are cool.
We have one last question in the chat. I think we'll do this, and then Omar, if you want to wrap up with a closure, have any closing comments, and then I guess people here, there's still food and beverages, and we can mix here yet, but I think we'll wrap up with the presentation after that.
Yeah, thanks, Luke. Yeah, I have actually two questions in the chat. One from Krishna Tripanthi, and Jim, you've alluded to this with your previous comments, but can you please, recently electric and hydrogen aircraft are in development. How would you anticipate icing certification requirements will change? So that's the first question from Krishna. And then the second one from Alan. Are there active projects and available findings on how climate change can potentially modify the long-used assumptions regarding characteristics of freezing conditions? Do we expect to see an increase in icing damage on engines that were certified long ago? And do we expect to see a change in regulations? So those are the last two chat questions.
I'll tackle that last one for one of my predecessors said that when we do icing certification testing, we actually expose the engine to more ice than it will see in 10 lifetimes. So we really do drastically over test the engine. And the reason we do that is because before the aircraft get its certificate to fly, you have to have a certificate for the engine first. But to get the certificate to go flying, you actually have to go flying. They actually do an in-flight icing test. Now, to hedge their bets, what they do is they do icing tests on wing. They take a wing section and they'll put it in an icing tunnel and they'll build up ice on it, and they'll actually take a mold of that ice accretion and they will make it out of plastic, and they'll go and they'll bolt it onto the wings of an aircraft and go flying with it to see whether or not the stability and control of the aircraft is significantly affected by that. And these pilots, man, they're
That would scare the hell out of me.
yeah. So they do that to get, well, they've done the wind tunnel test to show that the lift and drag coefficients and all those polars are within the normal operating range. So it's not like they're just flying it for the first time and not knowing. So they've got a lot of data to back it up, but they still go and they test that first. But ultimately, to get that certificate, they go flying with an FAA or EASA or Transport Canada inspector goes on the aircraft and they go flying. And in some cases, that usually it's the engine. If it's an engine that's being certified, the new engine is on one in one side, and an engine which has been certified, an older version or a different type, is on the other side. So if the new engine quits, then they still have the old one there. But the idea is that if the engine is tested far beyond what the aircraft is ever going to see, the pilot doesn't have to worry doing these flight tests that the engine is going to quit or give them a problem. It's now up to see whether the aircraft can handle the ice accretion and cause the aircraft to go into a stall or something like that. So fortunately, it's very hard to find the most severe icing conditions that we test to. They aren't that common in nature. And so they can go and find these test conditions to give them some satisfaction. So I don't see, that climate change is getting worse. I don't think that the actual conditions are getting worse. They're becoming more common. Whereas they may have been less hard to find, now they'll become easier to find those conditions. But the conditions themselves aren't going to be worse. So that I don't see that climate change is going to affect, but it will be more likely that you would encounter it. And I know many pilots. There's a lot of pilots flying around. They've never flown in icing conditions, and that's been the result. If you watch that show Mayday, there's a couple of examples where a plane went down in Buffalo and neither pilot had any experience flying in icing conditions, just because of where they've been flying in parts of the country where it wasn't very common, and now they're working in a cheap airline in Buffalo and where there's lots of icing conditions. So don't fly. Avoid Chicago. Avoid Detroit. Those are Newark. Those are some of the worst airports. Just a little tidbit. Free of charge. Sorry, what was the question?
Yeah, the second one, or the first question was regarding how electric and hydrogen architectures may affect certification requirements.
Yeah, well, I talked a little bit about the electric. You still have heat. You have to dissipate the heat. You have to cool it. There's a potential for ice accretion in the cooling systems there. Again, hydrogen, it's only going to affect, I think what Manfred mentioned here was possibly the stability of the combustion. If that is reduced, then it might make it more susceptible to flameouts as a result of ice ingestion. But the actual use of hydrogen itself, the icing is all at the front of the engine. So that's not going to change as a result of the fuel. It's just the stability will be a factor. But I think long before, there's not going to be hydrogen used in large aircraft forever. So it'll be mostly smaller aircraft where that will be a chance, because you'd have to tow another plane which is full of hydrogen to be able to fuel a large plane to get there. So that's just not going to happen. I think the dilithium crystals will come long before that. So But certainly for small commuter planes, there's a possibility of that hydrogen might make an entrance in the next 50 years. So, but it won't be an icing issue, I don't think.
Understood. Hey, thanks so much, Jim. Your presentation was very broad and also deep in a couple hours. So really appreciate that. You went into the historical aspects. You covered the certification regs, different types of icing, and the effect of icing on engine design, and how there's that tension, and increasingly so with the new engine designs, being more efficient, slower rotating fans, and then those are in opposition to the icing. So, and great answers to the multitude of questions. There was clearly a lot of interest in the room and online. So just wanted to thank you on behalf of CASI Ottawa branch, Luke, Jeff, the other co-chair, and myself for presenting. That was really enjoyable, really interesting, and just super fascinating. And hope to meet you in person someday. So
You have, Omer. We met at the last meeting. You got to get that Alzheimer's looked into.
Thanks. Yeah, good point. Thank you, Jim, and thanks for the reminder. And signing off for this session online. And thank you all to all the attendees, and again to Jim. So have a good night. Cheers.
Thank you.
Thank you, Jim.
Jim, thanks very much for your contributions to all this icing work over the years. It's I don't think people really understand how much you and your team have contributed.
Yeah, well, it's we've been doing it for a very long time, and I said I just passed the halfway mark a year ago, so I can coast for the next 39 years.
Well, thanks.
Cheers. Thanks, everyone.
Thanks. Bye.